Okay. So this is chapter 6 now, moving into section 6.1. So chapter 6, geometry, skipping over chapter 5. Chapter 5 is an interesting chapter about the growth, like linear growth versus exponential growth and quadratic growth. I'm sure I'll go into all sorts of stuff like that. So that's good for modeling real world problems. But we're skipping it, going into geometry because it's probably a little bit more real life applicable. So we've got chapter 6 and 6.1 in particular is called super vague. What does this even mean? Everyday geometry and applications. Now, sometimes the titles of these sections is like not really, I don't feel like it really describes what's in the section. We're going to be looking at angles. Okay, that's what 6.1 is about. We're going to identify some basic geometric structures like lines, points, rays, line segments. We're going to look at angles. We're going to look at triangles. And that's pretty much going to be what we're going to do in 6.1. The latter half of 6.1 is about trigonometry, which right angle trigonometry in particular, which is super useful in real life, but we are going to skip it. If it's something you're interested in, you can obviously go look that up on your own, right? Now, let me see here. My camera seems tilted. Is that better? I think so. Okay. Or is it that my handwriting is tilted and the camera was fine? That should be straight there. That's fine. Okay. So let's start off with some definitions for point, line, line segment, ray, and plane. We're not really going to talk about planes too much, but it still doesn't hurt to write down the definition. We denote points using capital letters. Let me first tell you that so that when you see me write one down, you understand that. So we could say this point P, capital P, a point has no dimension to it, so no width, no size, right? No width, length, or height, or shape, I should say, shape, no shape to it at all. It's just like a location in space, right? So if I said, you know, if that seems a bit abstract to you, but you know, if you were describing to me like how to get to a certain location, and I said, well, you know, what is the shape of the location? You might be like, well, that's a weird question because it's just a point, like it's a location. It doesn't have like a shape, right? It's just a location. Okay, a line is an infinite collection of points that extends infinitely in both directions, infinitely, I'll say in opposite directions. We denote it by using 2 points on the line, so just 2 random points on the line that we're going to label. So when I draw the picture, typically like we'll say like A and B, so I'll just pick some random point on the line, A, and then some point B on the line. And we denote it by writing AB together with this little line symbol above them. So it's like a little mini line above AB. A line segment is also technically an infinite collection of points. Technically, in between any 2 points, there's infinitely many things. No matter how much you zoom in, there's going to be infinitely many points. Between two specified points. And how does that differ from a line? How does that differ from a line? Well, it doesn't go infinitely in both directions. It doesn't extend infinitely in both directions. We might have some points C and then D, and that, oops, I wrote C twice, that's D. C and D, and the line segment is just this little piece of the line. I say it's still technically an infinite collection because there are technically infinitely many points here, but that's just kind of a little subtlety. You don't need to be too worried about that. We're going to denote it similarly to how we denote lines. So we'll write the letters together, C, D, and we'll just put a bar above them with no arrow on either side, right, to show that it is a line segment that is finite in both directions. Well, how should I say? It doesn't extend infinitely in both directions. It doesn't extend infinitely in either direction. Then we have a ray. If the book calls it a half line, that's okay. So it has a specified endpoint, whereas the line segment had two specified endpoints, right? But array has a specified endpoint. And just say this kind of in layman's terms here. Array is a half line with a specified endpoint, and the other end is infinite. So on the other end, we just get to pick some point and name some other point. So I could have, so the array EF, and I could, so here's E, and then where do I put F? Well, somewhere over here, somewhere, but it's kind of like a line on this side. So I'm just picking some arbitrary point to name the direction of this ray. And we denote it very similarly, just like this. And the direction of this ray is going to matter. So let me note that. This ray, EF, versus well, let's see. No, that's going to be confusing. Okay. Let me say it this way. This line segment I could name as AB, or if I wanted to, I mean this line I could name as AB, or I could name it as BA. No problem. It doesn't matter. Order doesn't matter there. This line segment here, CD, I could name as DC if I wanted to. No problem. This ray though, I can only write as EF. The direction matters. I cannot write it as FE because the direction of the ray tells me that it's infinite in the F direction, right? Not like this. So this is not correct. So that's an important thing to note there. So, and then finally a plane. So a plane is like a two-dimensional thing, no depth to it, right? It's just like a piece of paper, has no depth to it. It's a flat surface. And it does extend infinitely in all directions. Oops, directions. And we denote them with uppercase letters, kind of like a point. So I could say like maybe some plane here, and I could just call it like A. And this technically, does extend infinitely in all directions, so just can't really draw that, right? So maybe the way I'll draw it is just by putting arrows on each on each end. We're not going to do a lot with planes. Okay. So an interesting thing about geometry is most of the geometry that you learn in high school and what we're doing now and even beyond was all figured out and compiled by this Greek mathematician named Euclid like 2,000 years ago. And the book he wrote called Elements, or sometimes it's called Euclid's Elements. It's like a series of texts. They were used as geometry textbooks for math students. And, not just math students, but anyone who needed to do any geometry for like up until recently, like the 70s is when people finally stopped. I think it was like around the 70s, maybe a lot earlier. But for nearly 2,000 years, or roughly thereabouts, people were using his text to teach geometry, which is pretty cool. All right, let's do an example. It's just a little softball example here. With a line segment, given that KB is equal to 10 inches, so this is KB. By the way, I'm going to be drawing a line segment down here, so you'll see what KB is. BM is equal to 12 inches, and MC is equal to 13 inches. Find the length of KC. So notice I didn't just say find KC, I said find the length of KC, right? So just making a note there about that. So I've got a line segment split up into pieces here. There's K, B, M, and C. Okay, find the length of KC. Well, I see that KB is 10 inches in length, BM is 12 inches in length, and MC is 13 inches in length. So how do I find the length of KC all the way across? Well, I'll just add them all. 10 plus 12 plus 13 is going to give me 35 inches. Okay, so that seems super simple, and it is, but it's kind of making an important note that when you're dealing with line segments, you can do these kinds of things that make a whole lot of sense. Like you literally just add up lengths, right? It doesn't work with lines or rays, right? Because lines and rays are infinite in length. So the only time you can do something like this with adding or even subtracting the lengths of these geometric objects is, at least in this context, they have to be line segments. Okay, let's do some more definition stuff. I guess I can continue using this page. So I can say, two lines that lie in the same plane that never cross are called parallel. Maybe you've heard the term orthogonal before. Orthogonal is just like a generalization of the word parallel. Let's not get into it. You got two lines laying in the same plane that never cross, so they're like this. They're never going to cross. They're called parallel. When two lines intersect, an angle is formed, right? So that's how an angle is formed. When two lines intersect, well, actually more than one angle is formed, right? How many angles are formed? Let's just say angles are formed. You know, it's 4 angles, right? But really, how many unique angles? Let's let's keep going with this discussion. So when two lines intersect, angles are formed. Let's define what an angle is before we get into looking at the intersection of two lines. An angle is formed. Let's just talk about one particular angle. When two rays, so not two lines intersecting here, we've got two rays, have a common endpoint. And remember that endpoint is where they're finite. Have a common endpoint, which we call a vertex. So here's a picture of an angle. You got some ray, like maybe like AB, ray AB here, and then another ray that shares a endpoint with this. So A is the endpoint here. Maybe some other ray AC. Together, they create an angle. And this letter A here, this point where they're sharing that endpoint, we call that the vertex. How do we denote this angle? We can say angle A. Sometimes that's not enough info though, right? Just to call it angle A. So most of the time we'll say like something like angle ABC. Nope, not angle ABC. We'll say angle BAC. So that vertex point should be in the middle. So BAC, or we could also call it angle CAB. CAB. The point is that vertex should be in the center, right? And you should be reading them in order, either BAC or CAB. We say the measure of an angle. In other words, how do you describe the size of an angle? The measure of an angle, well, is the number of degrees. That's okay. I'm just kind of going off what the book says here. That's fine. The number of degrees that separate the two rays. How do we denote that? So if I say, like if I draw some angle EFG here, and I want to talk about, so that's a G, and I want to talk about its measure, and I say that, oh, in here it's 48 degrees. I would say M, little m for measure of angle EFG is equal to 48 degrees. That's how I would notate that. Recall that if I'm going too fast, since this is a recording, you can just pause the video, right? So normally I would spend more time on each page as I'm writing definitions and whatnot, but you can just pause. Okay, so now let's talk about different types of angles. Types of angles. We've got tiny angles, angles that are less than 90 degrees. We call them acute angles. Acute angles are angles with measure between 0 degrees and 90 degrees. Well, I should say less than 90, so it can't exactly be 90. So like the angle I just drew back here, angle EFG, since its measure is less than 90, between 0 and 90, this is an acute angle. Obtuse angles are angles with measure between 90 degrees and 180 degrees. I should say more than, so it can't exactly be 90 degrees. and less than. So it cannot be exactly 180. It can be like 179, 179.99999. And why am I making a point of that? Well, because we have two other special angles that when they exactly equal 90 degrees, when an angle is exactly equal to 90 degrees, then we say it's a right angle. Now let me give you a picture of an obtuse angle though, because I didn't actually draw one of those yet. Maybe something like this. Clearly this is obtuse because it's greater than a 90-degree angle. A right angle is exactly equal. No. A right angle has measure exactly equal to 90 degrees. And we often denote that with a little square in the corner of the angle. So maybe this is some angle X, Y, Z, and we denote it with a little square in the corner to show that's 90 degrees. Oh, by the way, I do my capital X's and Y's with bars above them. It's just like this habit, this weird habit I got into a long time ago because I had an instructor or a professor who I could never tell his capital X's and capital Y's from his X's and Y's. And that was super important in that class that I took with him. So I ended up doing that in my notes so that I would always be sure which was a capital X and a capital Y. So that's just like a habit I've gotten into. All right. So you don't have to do that. All right. And then finally, we have a straight angle. Has measure, and what's the last case? Has measure exactly equal to 180 degrees. So a straight angle is literally like a straight line, except it's still like a pair of rays. They're just pointing in opposite directions. So maybe ray C, D, E. So it's still two rays, DE and DC, but they're pointing in exactly opposite directions. And that would have, this would be a straight angle and it has measure 180 degrees. Okay, so far so good, just definitions and stuff. Now let me draw you a picture here, and I'm going to say a whole lot about this picture. I'm going to have, whoops, I didn't mean to draw through that. No, oh well. All right, so I'm going to have like 1, 2, 3, 4, 5 new, well, 4 new definitions coming from this picture. So let's now talk about two lines that are intersecting and talk about how their angles are related. Because this, when I take two lines and intersect them, not just two rays, but two lines, I'm going to create 4 angles. Let me call this A, I'll call this C, and I'm just going to take some other random line. Here we go, and I'll call this point B and D. And I've got to name the center point now, and I'll call it E. Okay. So I've created 4 angles. AED, DEC, CEB, BEA. And each of those 4 angles I could also name multiple ways, right? I don't want to get into listing all of them, right? We'd be here for a while. The point is that there are 4 angles here. Now, 2 angles that are across from each other are called opposite angles. So, or you could just say 2 angles that are opposite to each other are called opposite angles. That makes sense, right? So, where are some opposite angles on here? Angle AED is opposite to opposite is the vocabulary word here, to angle BEC. So AED is opposite to BEC. What else can I say? Angle DEC is opposite to angle, so this one, DEC, opposite to it, AEB. AEB. So that's what opposite means. And moreover, what can we say? You may already know this. What can we say about opposite angles? Opposite angles have equal measure. So that means if I were to plop down some measures on this picture, let's see what color. Okay. If I said, let's just make up an angle measure here. What does that look like? It's like 110 degrees, maybe, just to make it easy. 110 degrees. Well, that means this angle over here, the one opposite to it, is also 110 degrees. Similarly, DEC is opposite to AEB. So if those two have measure, what would they have to have? Since I've picked 110 here, I'm now limited. I have to pick the right angle here. And this is kind of getting into the next definitions that we're going to look at, but this would have to be 70 degrees because that's 110. I'll talk about that. But what the point I'm trying to make here is that these two angles are opposite to each other. What I name DEC and AEB, so they have the same measure. When two angles are opposite to each other like this, they have the same measure. Oh, where am I going here? Okay. Two angles that share a vertex and a ray are called adjacent. Now you might already know that adjacent literally just means two things that are next to each other. Like if you're sitting next to someone, you're adjacent to them. It just means next to. It's the fancy way for it. So an adjacent angle, I should say adjacent angles. There we go. Two adjacent angles are just two angles that are next to each other. So for example, angle AED, which angle is this adjacent to? It's adjacent to two of them. Is adjacent to both. It's adjacent to two angles. Which angle? Oh, let me get this picture. Here we go. Okay, AED is adjacent to, which angles is it next to? AEB, so this one. And what is AED adjacent to? It's also adjacent to this one, DEC. And I could do that for each one of these. I could describe angles that they're, I'm not going to do that for every single pair. Hopefully you're getting the point. It's just an angle next to the other angle, right? So this angle, AED, is adjacent to DEC. And it's also adjacent to AEB. And what do we say about adjacent angles? Never mind. I was about to write something that wasn't quite what I wanted to. Okay. So next comes the next two definitions. And let's see, I'll redraw the picture when I need to. All right. Two angles are called supplementary if their measures sum or add to 180 degrees. So for instance, back here, oh, come on. These two angles, AED and DEC, are supplementary because they add to 180. In fact, there's tons of supplementary pairs here, right, on this picture. This and this, this and this, this and this, this and this. Any two angles that are adjacent actually are going to sum to 180. In a picture like this, if the angles are next to each other, then they have to sum to 180. Okay. Okay. Two angles complementary are called complementary if their measures add to 90 degrees. All right, let's do some problems. Last little definition here. Two lines. Probably most of you guys are familiar with this one or will remember it as soon as I write it down. Two lines are perpendicular if they meet, I'm going to say it this way, if they meet at a 90-degree angles. If the angles at which they meet are all 90 degrees. Right angles. All right, now let's do some practice with these new definitions. Example 2. A lot of definitions in between the two examples. Example 2. Find the measure of angle EBD. Okay, here's the picture. I've got a straight angle A, B, C. And I've got a right angle going straight up right here. There's D. And then I've got another angle over here. Ooh, that is. So how do I know this is a right angle? There's your little box there. And that means this one on this side is also a right angle, right? Of course. And then this point E. And then I'm told that this angle measure here is 37 degrees. All right, cool. Now, what do I want to find? I want to find the measure of angle EBD. So I'm looking for this measure right in here. So I'll put a little question mark there. That's what we're looking for. Well, what can I say? Note that angle ABE, and angle, the one we want, EBD, are what? Complementary. Why? Because together they build a right angle, right? Their angle measures should sum to 90 degrees. So that means if I take the measure of angle ABE plus the measure of angle EBD, I will get 90 degrees. Because I know this angle right here is 90 degrees. So if I add this piece and this piece, I should get 90 degrees. I already know the measure of angle ABE is 37 degrees. I don't know the measure of this angle, right? That's what I'm looking for. So how do I solve for measure of angle EBD here? Subtract 37, right? So measure of angle EBD, subtract 37 from both sides, and I'm going to get 53 degrees. Right? Yes. Just subtracting 37 from both sides. That's the angle that needs to be put here, right, in order for this angle to become a right angle, for angle ABD to be a right angle. And I know that ABD is a right angle because its adjacent angle over here, DBC, is a right angle. Let me look at the problem I gave. Where am I? 6.1, 14. Yeah. Okay. Okay. Let me look at this picture for a second. Okay, so let's look at this picture. So this is example 3. Consider this picture. And I'm going to call it, I'll do X, Y, and Z again. X, Y, Z, Z. Okay, and let's say that the question is if the measure of angle XYZ is equal to, and let me think for a minute. I'm trying to think of numbers that won't work out real terribly. Yeah, that's fine. 10x plus 60. Oh, and by the way, this is measured in degrees, right? Then find, so that's not a 0, that's a degree symbol. 10x plus 60. This would end up just being some degrees. Find x if ray xy, oof, wait, I gotta be careful. I gotta call it ray yx, right? Ray yx is perpendicular to, so that little upside down T symbol, that means perpendicular to ray y z. I mean z, sorry. Forget. We call it Z. Okay. So that little symbol means perpendicular. That means that I want them to meet at 90-degree angles. So instead of just drawing a little square here to tell me that they meet at right angles, it's telling me in the problem that they meet at right angles by telling me that this ray is perpendicular to this ray. So what does this mean? How do I solve this? Well, they're telling me the measure of the angle, right? They're saying the measure of this angle is 90 degrees. So that means I take 90 degrees and I set it equal to 10x plus 60 degrees, literally setting it equal to the measure of the angle, and I'm going to solve for x. Now, since both are measured in degrees here, I can go ahead and drop the degree symbol and just treat this like a normal old equation. I'll go ahead and subtract 60 from both sides, and I'll get 30 is equal to 10x. And then I'll divide by 10 on both sides, and I'll get 3 is equal to x. In other words, x is equal to 3. That's it. Cool. So that's just like a nifty little problem that can be set up. Okay. Example 4. What other nifty little examples or problems can be set up? Okay, find the measure of angle 1, angle 2, and angle 3. So now I'm abandoning the letter representation for angles because that's what this problem does. You'll see problems like this in Hawks too. For whatever reason, they like to use numbers to denote angles when they're inside of triangles, which is what I'm about to draw here. Oof, wait, I want it to be like a little bit further. Doesn't really matter too much. Okay, and then this is 1, this is 2, and this is 3. So there's angles 1, 2, and 3. And now I've got to give you some other info. Let me say that this is 43 degrees, so that's 43 degrees, and this one is 48 degrees. And then this one up here, ooh, wait a second. Ooh, okay, I gotta make sure this works out right, because I'm changing the numbers from the book problem. This is number 17, 18, and 19 in 6.1, but I'm trying to change the numbers a little bit. I gotta make sure it works out right. Does it matter? No, it doesn't matter. Okay, good. So I'm going to say like, just slightly change it, 52 degrees. So that's 43 degrees, 48 degrees right there. It's 48. I know that's tiny. That's 48 degrees right there. And that's 52 degrees. So how do we find these missing angles? Well, the first thing I need to know is that the sum of angles in a triangle should be 180. The sum of the angles in a triangle is 180 degrees. So what does that mean for angle 1? Well, let's see. I should have 43 degrees plus 48 degrees plus measure of angle 1. So those three angles in this triangle should be 180 degrees. You see how I'm going to solve for angle 1 here, right? I'm going to combine these and then subtract them over. So that's going to be 91 plus measure of angle 1 is 180 degrees. I have to cover this up a bit for a second. And then measure of angle 1 should equal 89 degrees. Did I add right here? Let's see, 51 plus 40, 91. Yeah, okay. Cool. So now I know measure of angle 1 is 89 degrees. But now I also know that angle 2's measure is also 89 degrees. Let me say it like this. So here's my work for this, and now I'm going to take this off to the side for a moment. So I'm going to say measure of angle 1 is equal to 89 degrees by that rule that all three of these should add to 180. Measure of angle 2 is also going to be 89 degrees because they're opposite angles. They're opposite angles, so they should have the same measure. Now, how do I solve for measure of angle 3? Well, now I know that in the right-hand triangle, that measure of angle 2 plus measure of angle 3 plus 52 degrees should be 180 degrees by the rule for triangles, but I also know measure of angle 2 is 89 degrees. So I've got 89 degrees plus measure of angle 3 plus 52 degrees. Now I can solve for measure of angle 3. Just got to add these up together, and then I'll scoot them across. Oh God, is this going to work out right? Yes, it's fine. Okay, so adding these two together, that's 91, that's 141. So 141 degrees plus measure of angle 3 is equal to 180 degrees. Just taking the sum of these two. And now I'm going to subtract 141 to both sides, and I'm going to get 39 degrees. So measure of angle 3 is 39 degrees. Okay, so all that's being used here is the rule for the sum of the interior angles of a triangle should be 180. Then also the rule for opposite angles, they should be equal. And then again, the rule for the sum of angles in a triangle summing to 180. That's what I just used. Okay, that is it for section 6.1.